Hello. In this presentation, we will be going over how to qualitatively predict the behavior of systems of differential equations. By qualitative, I am referring to getting a general idea of what the solution looks like for various conditions. We use qualitative approximations when it is not possible to solve the equation exactly, or when doing so requires more effort than it is worth. Before we can qualitatively represent systems of differential equations, we need to review direction fields, which we covered earlier in the semester. So a direction field is a plot of the slope dy dx versus x and y for a differential equation. As an example of this, we start with the differential equation dy dx is equal to y squared minus 2y. This is selected because it does not include x in the differential equation, which allows us to do a two-column table relating y and dy dx, as opposed to a three-column table representing x, y, and dy dx, which requires a considerable amount more work. So to plot the direction field, we take our input, which in this case is y, we select a value. In this case, we will start out with -1, and we plug it into the differential equation. Plugging in -1 gives us parentheses -1 parentheses squared minus 2 times -1, which gives us a value of 3. We then continue by doing this for 0, which plugged in gives us a value of 0 for dy dx, 1, which plugged in gives us a value of -1 for dy dx, 2, which gives us a value of 0 for dy dx, and 3, which gives us a value of 3 for dy dx. The next step is to plot small lines that have this slope onto the coordinate axis. A line with a slope of 3 is going to be steep and it's going to be going up from left to right. We can then do this for each of the x values. In this case, I'm choosing to do 5 going across because that way it is enough to show detail without appearing too cluttered. For 0, the slope of the line of 0 is a flat horizontal line, and so we sketch these onto the x-axis. I realize this is a little bit difficult to see, however, there are small flat lines on the x-axis if you look closely. We do similar for y equals 1, this time with a slope of -1, meaning that going left to right it goes down. At y equals 2, the slope is 0, so these are flat lines. And for y equals 3, the slope is 3, so these are lines going up from left to right, similar to what it was in -1. And this is our direction field. By this, we can get, if we start at a point, we can then trace a path that the solution would go through on the direction field. And this is an example of a qualitative approximation. Next, we consider phase portraits for systems of differential equations. A phase portrait can be made from a direction field, and the process for it is very similar. One difference in a system of two differential equations is now, instead of just having dy dx, we have dx dt and dy dt. In this case, we are using the notation of x prime for dx dt and y prime for dy dt, although there are other notations out there. So, a note, some of you may recall from Calculus 2 that for derivatives of parametric equations, dy over dx was equal to dy dt over dx dt. And that's what we'll be using here. One annoying thing about this is we do have to, for most of these equations, plug in values for both x and y. Also, the other thing is because we have dx dt, these lines do not always go left to right. Instead, some may go from right to left, as if dx dt is negative, then it will go from right to left as x is decreasing. Anyway, plugging in these values and setting up as a fraction for this first system where we have x prime is equal to x minus 3y and y prime is equal to -y, we get the values as shown in the table. It is worth noting that I am leaving these in fraction form even when it is 0 over -1 and 0 over 0. In this case, 0 over 0 means there is no change. If we start out at the point 0 over 0, we will stay there for this system because dy dt is 0, so it's not changing with regard to the vertical, and dx dt is 0, so it's not changing with regard to the horizontal. So, using a phase plot generator that includes more values, we get the diagram shown below. Note that along the x-axis, we do have flat lines. So, if we look at the x-axis on this, that is going to end up being stable. It will never leave the x-axis. Also note that the arrows are pointing away from the origin, so this will be unstable. Any initial condition on the x-axis will move away. Similarly, there is actually a line at which it will approach the origin. So if we look, there are arrows from each side that will approach the origin. And similar to other phase plots, if we're slightly off of that, it will initially approach the origin and then it will go away to one side or the other based on whether we are above or below. Next, let's take a look at where we have x prime is equal to negative y squared and y prime is equal to negative x squared. Filling in the table gives these values. Putting it into a direction field sketcher and gives this pattern. I would like you to pause the video for about a minute and take a look at this direction field and see if you can predict some trajectories and identify what this is doing. Now that you've had a chance, you may notice that if we approach the origin on this line 1, 1, if we're above and to the right, we will come straight into the origin, and it actually will temporarily be stable there. On the other hand, if we're on the line 1, 1, and we are below and to the left, it will then move away. Other trajectories will actually go around the origin, and this will make trajectories where, unless you are on the line y equals x, you will end up going around the origin and just pass on by. So this is an example of a qualitative sketch, because solving this differential equation ends up being significantly more complicated. Something that I want to mention is that each differential equation and system of differential equations that we have done thus far on this video have been autonomous. What autonomous means is that any variable that appears in an equation also has its derivative apparent in the system. In this case, we had dx over dt and dy over dt. The variable t never appeared in either one of the equations on either one from the last slide. Instead, only x and y appeared, where each one of them was actually dependent on t. What autonomous systems allow us to do is they allow us to make a sketch of the general behavior because the time at which it starts is unimportant. Instead, the only thing that matters with regard to a system of two differential equations is what the initial point is in terms of x and y, or whatever variables we make equal to x and y. For that reason, for the remainder of this presentation, we will only focus on autonomous systems as they are much easier to approximate. So, a phenomenon that can be represented with an autonomous system is the rigid pendulum. This involves a mass hanging from a fixed length that is attached to a hinge. Now, in this system, we are actually not going to use x and y for what they may seem, because X and Y in this case are awkward. At any point, both X and Y are changing, whereas if you look at a pendulum, it is simpler to think of the angle of which it is from the middle and track the change of that. So a key element here, and please mention this in your discussion board posts if you would like to possibly earn extra credit, is the idea we used when we turned a single differential equation into two differential equations. You may recall that one technique that we used was to make the derivative of one variable as a second variable. In this case, we will do this. So in this case, we will make x be equal to the angle theta and y be equal to the derivative of the angle theta. What this does is this converts a second order differential equation that is complicated and very difficult to solve into two much simpler differential equations that can be made into a system. So doing so results in the differential equation x prime is equal to y, since y is the derivative of theta with respect to time and x is just theta, and then y is equal to c, which is a drag coefficient, over the length times mass, negative that times y, minus g over L times sine x. Of note, this is nonlinear since we have the sign of one of the dependent variables. And so this makes solving this analytically very difficult to do and in most cases not worth doing. Now, again, as a reminder, this is autonomous. Time does not appear in this. With regard to how a pendulum swings, it matters not when we start it. Instead, it matters where we start it, at what angle, as well as what the initial speed is. The initial angle would be x at 0, and the initial speed, that is the angular speed, would be y evaluated at 0. So now what we can do is we can choose values based on our situation for mass, length, gravity, and drag, and then we can sketch a direction field. Normally, we would choose this for a particular situation we wanted to model as a pendulum. In this case, we will be doing so arbitrarily. Simplifying the equations so that the constants are represented by single characters, in this case, omega squared is equal to gravity divided by length, and gamma is equal to drag over length times mass. The system of differential equations can be written in a simpler form as x prime is equal to y, and y prime is equal to negative gamma times y minus omega squared times sine x. To give a simple approximation of this, we will set omega to be equal to 1. We will then consider two separate cases of gamma is equal to 0.15 and gamma is equal to 0. A key distinction on these two cases is that when gamma is equal to 0.15, there is drag. This is more realistic, although the exact amount of drag is going to vary according to what the pendulum is. And then the second case is where gamma is 0, and so this is without drag. Given the fact that we want to get a large amount of direction field lines, we choose to use a direction field phase plot generator that plugs in values for x and y based on our parameters and produces direction fields. Doing so yields the following. Note that for illustration on this, we have phase lines, meaning lines that follow the direction field indicated on each of these. What I would like you to do right now is I would like you to first of all, look at the questions at right. So look at the questions at right, look at the direction fields, pause the video, and see if you can answer these. Again, you are encouraged to post answers to these on the discussion boards. Now that you've had a chance to look at these direction fields and think about the questions at right, let's discuss these lines. A key thing to be aware of here is that the y-axis does not represent position. Instead, the y-axis represents angular velocity. The x-axis represents the angle. A key thing, in this case, the origin would represent an angle of 0 with a velocity of 0. So think about what it means for a pendulum to have an angle of 0 and an angular velocity of 0. This would be the pendulum sitting still at the base. This would be stable because this is not going to move unless there's an outside force acting. And again, this system of differential equations is independent of outside forces. Now, for one option, we can start by raising the pendulum to a particular angle and then releasing it. This is shown by the point where the point indicated on the one on the left with drag, and on this one indicated on the point on the left without drag. Note that without drag, this makes a circular trajectory. Let's think about what each point on this trajectory means. The point on the left is it raised to a particular angle. Once we release it, it gains velocity, but it decreases in angle. It eventually leads us to the point here where our angle is at 0. However, our angular velocity is negative, meaning it's continuing to travel away from where it started. It then will climb up to a negative angle and eventually run out of angular velocity. So in this case, at this point, we have an angle opposite to what we started out with, but also 0 angular velocity. Similar to what happened earlier, it then speeds up in the other direction and gains a positive angular velocity when it hits 0, and the process repeats. Note that this trajectory is a circle, and what that is meaning is that we have a constant trade-off between angle and angular velocity that repeats. This would be like the grandfather clock that continues going back and forth repeatedly. And this is stable. Without drag, this will occur forever. Now, before continuing, think about what would happen if there was drag involved in this situation. Would it continue in a cycle like that? Realistically, what would happen with some amount of drag to a pendulum eventually? Okay, eventually, all motion on Earth will stop due to drag. It may take a long time, however, it will stop. Moreover, the pendulum with drag will not climb to the same angle that it started out as. It will get up to less. This is the entire idea that means that on a half pipe with a skateboard, eventually you won't be moving anymore. Even if you stay perfectly in line, you will go up to less and less height as you go. This is represented by the spiraling trajectory here, where as time goes on, this slowly gets towards the origin and the point at which all motion stops. And so we're spiraling in to eventually where both the angle and the angular velocity are 0. Now, for a different scenario, consider taking the pendulum up to 90 degrees, meaning, or actually, correction, taking the pendulum up to 180 degrees. Think about what 180 degrees means when you're measuring an angle from the origin. At 180 degrees, you are exactly above it. So what that means is now it can go in the other direction. So it can actually make potentially circles. That is, if there's no drag. So in the case of this trajectory right here, we would start at this angle, and instead of coming back towards the way that it was when we moved it up there, instead it goes in the other direction. And potentially this would then create a new path. On the other hand, If there's drag, eventually it will slow down and eventually it will come back in. That's another key difference. So this has been an example of how phase plots can be used for nonlinear systems of difference equations for approximations. The goal of this was to show you, to some degree, the meaning of direction fields and give you an idea of how these can be applied. For this assignment, please post a reply to this to the discussion board, which gives a description of the video and answers to some of the questions and/or questions of your own. And please be ready to respond to classmates. Thank you for watching. Have a great weekend.